Okay, today we need to talk about slant asymptotes, and we're also going to talk about how we can graph a rational function and maybe predict a little bit more what they're going to look like instead of just guessing. Up to this point, all of our asymptotes have been either horizontal or vertical. Well, now we're going to talk about a slant asymptote, and I think you can probably guess what that's going to mean. It's going to mean that the asymptote is slanted. So we may have something like this where we have a slant asymptote and then a vertical asymptote, and then maybe the function is kind of sandwiched in between like that. And that's what we mean by a slant asymptote. Now there is a specific situation where these show up. They don't just show up on any old rational function. A slant asymptote, we'll start here with a note. Slant asymptotes occur when the degree of the numerator is exactly 1. Exactly 1 more than the denominator. And there's one other thing we need to point out. We'll just make another note here. We find the equation of the slant asymptote using division, which is one of the other reasons why we just spent some time learning synthetic division and long division, is for situations just like this. All right? So best thing to do is just tackle an example here so we can see what this looks like. Let's say that my function was x squared minus x all over x plus 1. And we wanted to graph this thing. And of course we need to start by finding some asymptotes. The vertical asymptote is going to be easy, right? The vertical asymptote, we set the denominator equal to 0 and solve it. So I know that I have a vertical asymptote at -1. Now, let's be cautious though. Would anything have factored out at the top that would make that go away? I don't think so, because if I factored this top, remember we talked about that, it becomes x times x minus 1, so nothing will cancel. All right, so we're okay with that. We don't need to worry about that. But we do have the situation where the degree of the numerator is exactly 1 more than the degree of the denominator. Now, before we go that route, is there a horizontal asymptote? No, there's no horizontal asymptote, no ha, okay, because the degree of the numerator is bigger than the degree of the denominator. So we do have a slant asymptote. How are we going to find that? We're going to use division. Now, don't I have a nice x plus 1 here that I can use synthetic division with? I can't. So we may as well do it the easy way. So we set up our box, and I'm going to have a -1 on the inside, because remember we always change the sign of that thing. And then inside the box I put my coefficients. 1, the coefficient of x is -1, and then I need to put a 0 for the constant at the end. and we do our synthetic division. Bring this down, there's a 1, multiply, this is -1, this is -2, multiply, this is +2, I add, and I get a remainder of 2. Okay? Well, so technically what do I have here? I have y equals x minus 2 plus 2 over x plus 1. That's technically what I have. But what we do in terms of this little remainder is we just don't use it. It's considered insignificant. Everybody's greatest fear, to be insignificant. But that little thing at the end is insignificant in the grand scope of things. So our slant asymptote has an equation of y equals x minus 2. Isn't that just a nice little linear? Let's make a little sketch here of our asymptotes. I have a vertical asymptote through -1. So I have a vertical asymptote right here through -1. And then I have a slant asymptote, which is just a linear. We said it was x minus 2. So that means its y-intercept is -2, and its slope is 1. So I'm going to go up 1 over 1, up 1 over 1. I could come down 1 over 1. And I'm going to have this slanted line, and that is my slant asymptote, y equals x minus 2. This is my vertical asymptote, x equals -1. Now, you might be asking, where is the function? You know, where does it fit in between those asymptotes? And so what we're going to do now is we're going to talk about a process to find that out. Okay? Instead of just completely relying on the graphing calculator and looking at the graph, we're going to look at some analytic or algebraic ways to find these. Okay? So if I want to graph a rational, and we're talking about any rational, we're talking about the ones we've done the last couple days, as well as our new ones with the slant asymptotes. Here's some steps. Number 1, find all the asymptotes. And I think that's obvious. Okay? If I've got a rational function, I've usually got an asymptote. Number 2. Now this is the one you may not have thought of. Find my x and y intercepts. Because if I know where the function is going through the x and y axis, I can start getting an idea for what it's probably doing. All right? Now, for the x-intercepts, you know, we're dealing with a rational function, a fraction function that's ugly. But if you think about our steps, you know, if I have, whatever, x plus 1 over 5x minus 3 equals 0, if I solve that, doesn't this thing just go away? Wouldn't I multiply both sides by the denominator, and that thing would go away? So if I want to find the x-intercepts on a rational, all I have to do is set the numerator equal to 0. If I want to find the x-intercepts, all I have to do is set the numerator equal to 0. If I want to find the y-intercepts, all I have to find, I just have to find f of 0. Because if the x-coordinate is 0, all right, if the function exists there, That's going to be a y-intercept, okay? So, now, the next thing we should probably do is sketch my asymptotes. Sketch my asymptotes and intercepts. And one more thing. The asymptotes and intercepts will help us a lot, but we might need to find a couple of in-between function values. That's what I like to call them. Let's find some in-between function values, just to kind of confirm what we think is true. Okay? So we're going to walk through the whole process of doing this on a rational function, and this one will have a slant asymptote, so let's go ahead and get going here. Analyze and sketch a graph. So you're going to have a rational function. Let's say it looks like this. F of x equals x squared minus x minus 2 all over x minus 1. Okay, so let's find our asymptotes. First, vertical asymptote is easy. Vertical asymptote, I said x minus 1 equal to 0, so it's x equals 1. All right, that's easy. Are there any horizontal asymptotes? There's not, because the top power is bigger. So let's go to the slant asymptote. For the slant asymptote, I need to do division. So I can once again use synthetic division. We want to use synthetic anytime we possibly can. So I'm dividing this time by a 1, since this is a minus. And then my coefficients are 1, -1, and -2. And I do my synthetic division, bring down the 1, multiply, that's 0, multiply, that's 0. -2 is a remainder, which we know is insignificant. So my slant asymptote equation is just y equals x, because there was no, plus or minus a number because of this 0. So that's the equation of my slant asymptote. So how about some intercepts? Okay, so we're going to do the second. We've completed step 1. Let's do step 2. Step 2 and find some intercepts. So I said for x-intercepts, set the numerator equal to 0. X squared minus x minus 2 equals 0. That one will factor, I believe, pretty easily. X and x, minus 2 plus 1. So it looks like I have, my microphone came off. Intercepts at x equals 2 and x equals -1. Those are x-intercepts, okay? Y-intercepts, okay, for y-intercepts we need to find f of 0. So that means I plug 0 into the function, and I have 0 squared minus 0 minus 2 all over 0 minus 1. So I'm left with -2 over -1. I have a y-intercept at positive 2. So I've got some pieces now, all right? And let's go now to sketching a graph, and we're talking about doing this manually. 1, 2, 3, 4, 5. I'll just go about to 5 on both. Maybe I'll go to 6. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we said that we had a vertical asymptote at 1 and a slant asymptote of y equals x. So I know here at 1, I have a vertical asymptote. I know that I have a slant asymptote that is the linear line y equals x. And now this is where the intercepts can help us, because we had intercepts at 2 and negative 1. Okay, so now I know there's an x-intercept here, and there's an x-intercept here. All right, and there's a y-intercept at 2. So I know there's a y-intercept at 2. So we've got a little idea of what this thing might look like, but now what we can do is use some in-between values. And this is where the graphing calculator can help us. This is where the table can help us. Now, let's look at our graph. Let's kind of pick some values we might want to know. Yeah, wouldn't it be nice to maybe come over to, like negative 6 and get a value, right? And, when we get really close here to 1, maybe it would be nice to know something really close to 1, like 0.9 or something like that. And then maybe do one on the other side at 1.1. And then maybe we'll come over to, positive 6 and get a value, okay? And we may as well be efficient and use the graphing calculator. So we're going to put our function in. Make sure that you use parentheses for the top and bottom. So my function is x squared minus x minus 2, that's my numerator, divided by my denominator in parentheses, which is x minus 1. And this is a great place to go to my table setup and use ask. Okay, make sure that in your table setup you have your independent variable at ask, and then we'll just plug in the ones we want. So you go to your table. I've got some other junk in there. I need to get that out. Okay, so we said, at our graph, I wanted negative 6. So there's x-coordinate of negative 6, and there's my function value. And then we also said that we wanted to get really close to 1. So we said, why don't we do 0.9? And we have that value. And then we wanted to go on the other side of 1, so we'll do 1.1. And we'll see what function value we get there. And then we said maybe we'd go farther to the right and try positive 6. Oops. Okay, 5.6. So what we have now is some in-between values to help us out. I'll just kind of paste that in. Wouldn't it be nice if you could do that in your notes? So look what we've got. I know that negative 6 has a function value of negative 5.7. So here's negative 1, 2, negative 3, negative 4, negative 5. I know that I'm down here. Okay? And I know that positive 0.9 has a value of 20.9, so I'm way up here someplace. Okay, actually off of my graph. And positive 1.1 on the other side of the asymptote is way down here someplace at negative 18.9. And the value for positive 6 is up at 5.6. You know, this point is 6, 5.6. So now we've got a really good idea of what this thing does. Okay? This function is going to be one of these functions that is sandwiched in between the asymptotes, goes through that intercept, comes up and goes through that point, like that. And so when we talk about analyzing a rational function, that's the process that we follow, and we're going to stop there for today.